At 8:51 in the evening on June 5, 2021, the ground beneath Oregon's highest peak moved. Deep within the Earth, just 4 kilometers south of the summit of Mount Hood, a section of the planet's crust fractured. The energy released was a magnitude 3.9 earthquake. For the volcano, it was the most significant single tremor in nearly 2 decades. A jolt from a sleeping giant. 50 miles to the west, in the city of Portland, across a metropolitan area of 2.5 million people, life went on. Dinners were finished. Shows were watched. The sky darkened over the skyline. They felt nothing. Not a rattle, not a tremor, not a moment's pause. The strongest seismic event to strike their iconic mountain since 2002 happened right next door, and an entire city was completely, blissfully unaware. Before we go any further, think about this. When you hear the words earthquake at a volcano, what is the first image that comes into your mind? Magma? Eruption? Disaster? Let us know in the comments. The scientific reality is far more complex and a lot less cinematic. The data from the quake hit the Pacific Northwest seismic network in fractions of a second. Inside the Cascades Volcano Observatory, computer screens lit up. For the seismologists on duty, this wasn't panic. It was a puzzle, an expected one. Most people who watch our videos forget to subscribe. Don't be one of them. Hitting that button is the single best way to support this channel and make sure you don't miss our next investigation. It's fast, free, and frankly, it's essential for us to continue making these deep dives. Do it now, before the next tremor hits. Let's begin. This single event, this magnitude 3.9 shudder, was a test. Not a test of the volcano's stability, but a test of our understanding. A test of the instruments, the models, and the scientists who spend their lives listening to the subtle language of the Earth. And what that language said in that moment was not what most people would ever assume. It was not a sign of impending doom. It was something else entirely. The question is, what? And why should a quake that nobody felt matter at all? When an earthquake strikes a volcano, the first few seconds of data are everything. Instantly, computers at the USGS generate something that looks, to the untrained eye, like a black and white beach ball. It's officially called a fault plane solution, and it is a mathematical portrait of the forces that just moved the Earth. It is the single most important clue scientists have for decoding a volcano's intentions. The pattern on that beach ball tells them whether rock was compressed, sheared sideways, or pulled apart. For the June 5th quake, the beach ball solution was immediate and unambiguous. The crust was being pulled apart. This was what seismologists call a normal fault event, a signature of regional extension. The land itself was stretching. This was not magma shouldering its way toward the surface. This was not the violent fracturing that precedes an eruption. It was something far more common and far less threatening. For a scientist like Dr. Seth Moran, now the acting scientist in charge at the Cascades Volcano Observatory, this result was confirmation of a long-understood pattern. He and his colleagues at the CIVO are the detectives of the Cascade Range, tasked with distinguishing a cry of distress from a simple geologic sigh. The information statement they released was calm and deliberate. The earthquakes, they said, are associated with regional faulting and are not a sign of changes in volcanic activity. That distinction is the only thing that separates scientific monitoring from public panic. The location of the quake was the second critical clue. The epicenter was pinpointed 4 kilometers south of the summit, at a depth of 4.3 kilometers below sea level. For Mount Hood, this is the sweet spot. Over the last 30 years, the vast majority of seismic swarms have clustered in this exact same zone, a region roughly 4 to 7 kilometers south of the main conduit that feeds the volcano. In a formal statement, the CIVO noted how typical this was, explaining that it is rare to see swarms occur directly beneath the summit. Think about what that means. The shaking isn't happening where the magma is. It's happening next to it, in pre-existing fault lines that are being stressed not by the volcano itself, but by the colossal, slow-motion tectonics of the entire Pacific Northwest. The entire region is being contorted by the Cascadia subduction zone. The 600-mile-long megathrust fault offshore where one tectonic plate is being driven beneath another. That grinding collision squeezes, stretches, and cracks the continental crust for hundreds of miles inland. Mount Hood is just a bystander caught in that continental crossfire. The small, shallow earthquakes are the creaks and groans of a landscape under immense, constant pressure. This understanding is startlingly new. For decades, these faults were hidden, buried under forests and ancient lava flows. It was only with the pioneering work of geologists like Ian Madden at the Oregon Department of Geology and Mineral Industries, or DOGAMI, that the true complexity of the system began to emerge. Using a technology called LIDAR, which uses laser pulses to create a bare earth model of the landscape, Madden and his team were able to digitally strip away the trees and soil. What they found underneath was a web of previously unknown fault lines crisscrossing the Oregon Cascades, including the Mount Hood fault zone itself. The quakes weren't random. They were happening on mapped weaknesses in the crust. Weaknesses that have been there for thousands of years. The M3.9 wasn't a new threat appearing. It was an old feature reminding us it was still there. This has happened before, and it will happen again. The June 2021 event wasn't an isolated incident. It was the main shock of a classic Mount Hood swarm. A flurry of smaller foreshocks preceded it, and dozens of tiny aftershocks followed in the hours and days after. This volcano breathes in swarms. They are its normal rhythm. Just 5 months earlier, in January 2021, an intense swarm of over 100 tiny earthquakes had rattled the same region south of the summit, with the largest topping out at a modest magnitude 2.7. No one felt those either. They were instrument-only events, whispers picked up by the sensitive seismometers dotting the mountain's flanks. But to find a true benchmark, you have to go back to June 29, 2002. On that day, a magnitude 4.5 earthquake struck, centered in almost the exact same location, about 4.5 kilometers south of the summit. In seismic terms, an M4.5 releases over 30 times more energy than an M3.9. That quake was felt. Light shaking was reported in Government Camp, the small mountain community nestled on Mount Hood's southern slope. It rattled windows and nerves, a brief but sharp reminder of the power simmering below. Even then, 50 miles away in Portland, the reports were negligible. A few people in quiet high-rise buildings might have noticed a faint sway. But for the vast majority of the city, the event passed without notice. The 2002 quake triggered a similar scientific response. The fault plane solution showed the same tectonic stretching. The location was the same. The conclusion was the same. The mountain was not waking up. It was just adjusting to regional stresses. What the 2021 quake represented was the loudest of these adjustments in 19 years. A significant data point in a long, repeating pattern. This pattern is older than our ability to measure it. The volcano we see today, known as wy'east to the indigenous peoples of the region, has been dormant for over 2 centuries. Its last major eruptive period, a phase geologists call the Old Maid period, produced lava domes and pyroclastic flows near the summit. That activity sputtered out somewhere between 1781 and 1801. It stopped just 4 years before the Lewis and Clark expedition passed through the Columbia River Gorge in 1805, giving the world its first written descriptions of the peak. They documented a quiet, snow-covered mountain. They had missed its last fit of anger by a historical whisper. We have only ever known Mount Hood in its quiet phase, a phase punctuated by shakes and shudders that are echoes of a far larger geologic battle. So we have a mountain that shakes regularly, but hasn't erupted in over 200 years. What do you think is the bigger threat, the shaking we can't feel, or something else entirely? Comment below. Your perspective matters. The intense focus on earthquakes, on the ground shaking, is a fundamental misreading of the danger. Portland's real threat from Mount Hood isn't seismic. It isn't a tremor that will topple buildings 50 miles away. An M3.9 is far too weak. Even the M4.5 from 2002 caused no damage. The city's true vulnerability flows down from the mountain not as a shockwave, but as a river. The real danger is a lahar. A lahar is not simply a mudflow. It is a terrifying, fast-moving slurry of volcanic mud, rock debris, and water that can rush down river valleys at speeds approaching 100 kilometers per hour. They have the consistency of wet concrete and the destructive force of a freight train. They can carry house-sized boulders, uproot entire forests, and bury everything in their path under dozens of feet of gray, suffocating sediment. This is the work of scientists like Dr. John Major, a research hydrologist who was appointed scientist in charge at the CIVO in 2021. His expertise isn't in deciphering the shakes from a beachball diagram, it's in calculating what happens when a small eruption or a partial collapse of the volcano's summit instantly melts the magnificent glaciers and snowpack that cling to its slopes. That sudden release of water is what mobilizes loose rock and soil into a devastating lahar. Geologists like William E. Scott, now an emeritus scientist with the USGS, have spent their careers mapping these hazards. The geologic maps of the Mount Hood region are not just lines on paper, they are predictions. They show the paths of ancient lahars that have swept down these same valleys time and time again. The evidence is written into the landscape. For Portland, the primary vector of this threat is the Sandy River Valley. A significant lahar originating from the west side of Mount Hood would funnel directly into the Sandy River, surging downstream, overwhelming its banks, and potentially inundating communities and infrastructure all the way to its confluence with the Columbia River, on the very edge of the Portland metro area. The trigger for such an event doesn't even need to be a full-blown eruption. A small steam explosion, a localized landslide, or even a period of intense, rapid warming could be enough to destabilize a portion of the glacial ice and unleash a flow. The M3.9 earthquake was harmless, but the 11,249-foot mountain, with its 12 named glaciers holding millions of tons of frozen water, is a permanent hazard hanging on the horizon. The quake was a distraction from the real, quiet, and far more potent threat. If you know someone who lives in the shadow of a volcano, maybe in Oregon, Washington, or anywhere else, share this video with them. The real risks are almost never what you think they are. And please, hit that like button if you're learning something new about the forces that shape our world. It helps more than you know. The story gets stranger. The triggers for Mount Hood's earthquakes are not just the deep, slow grinding of tectonic plates. Some of them are caused by something far more gentle, something that happens every single year. The melting snow. Scientific studies of the volcano have revealed a bizarre phenomenon known as hydroseismicity. It is a process where water can literally cause earthquakes. As the massive winter snowpack on Mount Hood melts during the spring and summer, the water doesn't just run off into streams. A portion of it percolates deep into the ground, trickling miles down through cracks and fissures in the volcanic rock. As this water reaches the deep, pre-existing fault zones, the same ones that are under regional tectonic stress, it begins to fill pores in the rock. This dramatically increases what geologists call pore fluid pressure. Imagine trying to slide two dry bricks past each other. They stick. Now imagine squeezing a layer of oil between them. They slide easily. The water acts as a lubricant on a continental scale. It reduces the friction holding the fault locked in place, allowing it to slip. This process explains why Mount Hood often experiences an uptick in small seismic swarms during the late summer months. The meltwater from May and June takes time to travel miles underground. By August and September, it has reached the critical depth, lubricating the faults and triggering bursts of micro-earthquakes. Water, born from ice on the summit, is causing the rock to break almost 3 miles below. It is a stunningly interconnected system where the weather on the peak directly influences the geology deep within. This process, hydroseismicity, is yet another piece of evidence that points away from magma as the primary driver of the volcano's constant chatter. The mountain is creaking under its own weight and the changing of the seasons. I know we talked about this earlier, but I have to mention it again. A huge number of people watch these documentaries, learn a ton, and then completely forget to subscribe. If you are finding this deep dive fascinating, you have to hit that button. Seriously, the way the platform works, it probably won't show you our next video if you don't. Don't let an algorithm decide what you get to learn. So while Portlanders stare east at the majestic and occasionally trembling form of Mount Hood on the horizon, they remain oblivious to an even greater geological irony. The city itself, the one that couldn't feel the M3.9 quake from 50 miles away, is built directly on top of its own volcanic field. They aren't just next to a volcano, they live on top of dozens of them. This is the boring volcanic field. It is a sprawling, dormant network of over 80 small shield volcanoes and cinder cones that stretches across the Portland Basin. These are not towering stratovolcanoes like Mount Hood. They are smaller, more subtle landforms that have been so thoroughly integrated into the urban fabric that most residents don't even recognize them as volcanoes. Famous Portland landmarks like Mount Tabor and Rocky Butte are not just parks with nice views. They are extinct volcanoes. The city's West Hills are composed of ancient lava flows. People drive over them, build houses on them, and hike trails across them every single day, completely unaware of their fiery origins. The last eruption in the boring volcanic field was over 50,000 years ago. So the threat is effectively zero. But the irony is profound. The citizens of a city built atop a volcanic landscape spent a sliver of time in 2021 worrying about a tiny tectonic earthquake 50 miles away that posed no threat, while they drank coffee on the slopes of a much closer, much older, and much more intimate volcanic relative. It is a perfect illustration of how our perception of risk is often shaped by what is spectacular and distant, rather than what is mundane and right under our feet. The M3.9 quake at Mount Hood wasn't a danger to Portland, but it served as a powerful reminder that the entire region is a product of volcanic and tectonic forces that are still very much at work. As of the summer of 2026, the story continues to evolve. The volcano has remained quiet in the years following the 2021 swarm. In its weekly update from July 3, 2026, the Cascades Volcano Observatory confirmed that Mount Hood remains at a normal volcano alert level and a green aviation color code. This is the lowest, least threatening status. There have been no earthquakes exceeding the June 2021 M3.9 event. The background chatter, however, persists. Between December 8th and 13th, 2023, another small swarm of micro-earthquakes occurred, none larger than a magnitude 1.5, all of them completely imperceptible. They served as another confirmation of the mountain's ongoing hydrothermal and tectonic activity. A tiny M1.7 quake was recorded on July 1st, 2026, a few kilometers north of Mount Hood Village. The mountain continues to sigh, to stretch, to adjust. It is never truly still. And the science never stops. A major scientific field expedition was planned for July of 2026 at Mount Hood as part of the SZ4D initiative, a nationwide project to study subduction zones in 4 dimensions. Using drones and advanced geophysical instruments, researchers aim to map ancient pyroclastic deposits, trace hidden fault lines, and gather new data on landslide risks. They are actively trying to piece together the mountain's history to better forecast its future. It is a race to understand the system before it does something unexpected. The work of Dr. Moran, Dr. Major, Ian Medine, and hundreds of other scientists is part of a continuous effort to translate the planet's subtle warnings into actionable knowledge. Alright, this is your third and final warning. If you've made it this far into the details of hydroseismicity and the boring volcanic field, you are clearly one of us. You belong here. Hit subscribe. You know you want to. Don't make me send a geologist to your house to explain fault plane solutions in person. The silent earthquake of 2021 was never the real story. It was a symptom. It was a single data point in a much grander and more complex narrative. The real story is the mountain itself, wy'east, a massive, active stratovolcano that sits as a breathtaking backdrop to a major American city. Each year, between 10,000 and 20,000 climbers attempt to reach its summit, making it the second most climbed glaciated peak on the entire planet. They walk across the very glaciers that could one day become the source of a devastating lahar. They ascend past the vents that last breathed fire 2 centuries ago. They stand on a summit that is a cork in a bottle of immense geologic potential, all while the ground beneath them shifts and stretches in ways they cannot feel. The magnitude 3.9 earthquake was not a warning of an eruption. It was a reminder that the peaceful, static landscape we see every day is an illusion. The ground is not solid. The mountains are not permanent. They are living, breathing systems operating on a timescale that dwarfs a human life. The quake that Portland never felt accomplished something profound. It forced us, for a moment, to listen closer to a mountain that is very much alive and has a